We're going to continue our study of linear equations by talking about linear functions and some of their applications. So let's start with function notation. So in many applications, we can express a situation using a function where we express y in terms of x. And in such a situation, we call x the independent variable and y the dependent variable. Now, to name functions, we use function notation so that we can show what the independent and dependent variables are. So for example, here we have f of x equals 5 minus 3x, which shows you that f of x depends on x. So that notation, f of x, if you just look at the left, even without knowing what the rule or the expression is, you know that it depends on x. Now, we can express the input and output of a function more easily when we use function notation as well. So if we have f of 1 equals 2, that means that when you put 1 in there, you get 2. So this is kind of a shorter way of having to write when x equals 1, y equals 2, where x is the independent variable and y is the dependent variable. It's much easier to just write f of 1 equals 2, and all that information is encapsulated there. So we can apply function notation to any function, but in particular, we are going to be looking at linear functions today. So f of x equals mx plus b instead of writing y equals mx plus b. So here's example 1. We have g of x equals negative 4x plus 5. Find g of 3, g of 0, g of negative 2, and g of b. Let's start with g of 3. Now all we have to do to find g of 3 is to simply plug 3 in for x in the expression. So we have negative 4 times 3 plus 5, so negative 12 plus 5, which is equal to negative 7. We can do the same thing for the rest. So g of 0 is negative 4 times 0 plus 5, which is equal to 5. G of negative 2 is equal to negative 4 times negative 2 plus 5, which is equal to 13. Now if you have g of a variable, and it's not x, it's b, for example, all you would do is write the same thing, but instead of writing x, you'll write b. So this would be negative 4b plus 5. And that's as simplified as you can get that expression. Now, one very common place where linear functions are used are in supply and demand curves. So when we talk about supply and demand curves, it's important for us to actually understand the idea of supply and demand before we start talking about the linear functions that go along with these applications. So key things to know. First thing is, as the price of an item increases, consumers are less likely to buy the item, so the demand for the item decreases. Okay, so if something becomes more and more expensive, then consumers are not as likely to buy it, which means that the demand for that item, since there are fewer consumers, the demand decreases. So if you were to make a chart of this, if this were the price and this were the quantity of the item that's out there, then what this is saying is as the price increases, consumers are less likely to buy the item, so the demand for the item decreases. So this is what we call the demand curve. So as you can see here, when the price is very high, which is on the far left, then the demand is small, so the quantity is high. As you move further along towards the right, as the price gets lower, then that means consumers are more likely going to buy the item, so the demand is going to increase, which means the quantity of the item that's out there is much lower. Now when we talk about the supply, as the price of an item increases, producer, so this is on the other end. So the first end, the demand, is on the consumer end. The supply end is on the producer end. So say you're producing the item, and if the price of an item increases, then producers are more likely to see a profit in selling the item, right? You are more likely to want to sell something that's a higher price than something that's a lower price because you're going to get more from it. So, as the price of an item increases, producers are more likely to see a profit in selling the item, and so the supply of the item increases. That means there are more people producing it, so the supply of that item is going to increase. So if we were to draw our supply curve, or our supply line, this would be it. And you can see on the far left, if the price is very low, there's not a lot of profit in selling that item. And so not a lot of people are going to be likely to want to produce and sell that item. However, as the price goes up, the people who are producing the item will want to sell that item because they will profit more from it, so they will produce more of that item. Now, it's important to understand how the supply and demand curves relate to one another. So, when the demand of the item decreases and the supply of the item increases, the result will be a surplus. Right? So if some item is out there and there's not a very high demand for it, but the supply of the item just keeps coming, they keep producing it, then you'll end up with a surplus. So where does that occur? That occurs in this half of the graph here. Now, on the other hand, when the demand of the item increases and the supply of the item decreases, the result will be a shortage. So in other words, when more consumers want this item, but there aren't enough producers producing the item, the supply is decreased, then there are more people who want the item versus people supplying the item, and so you'll end up with a shortage, and that happens in this half of the graph. Now, obviously, neither are ideal situations. The most ideal situation is to be right there in the middle. The equilibrium price of the item, so the price at which you set the item at, is the price found where the supply and demand graphs intersect, where you won't have a surplus or a shortage. You'll have just the right amount, the equilibrium price. So this point right here is the ideal point that we want to be at. Now, the equilibrium quantity is the actual number of that item that is demanded and supplied at that same point where you won't end up with a surplus or shortage. So you'll notice that this point here is in fact a point on the graph, and along the x-axis here we have the quantity, so that would be the equilibrium quantity, versus the y-coordinate of that point, which is the equilibrium price. Let's take a look at an example. So suppose that Greg Robin, manager of a giant supermarket chain, has studied the supply and demand for watermelons. He has noticed that the demand increases as the price decreases. He has determined that the quantity in thousands demanded weekly, Q, and the price in dollars per watermelon, P, are related by the following linear function. Now notice here, we've written it in terms of P and Q and D, which is going to represent the demand. So the demand depends on Q, is really what this is saying. So P is equal to 9 minus 0.75 Q. Part A says, find the quantity demanded at a price of $5.25 per watermelon. Part B, Greg also noticed that the quantity of watermelons supplied decreased as the price decreased. Price P and supply Q are related by the linear function that's given here, and again this is given as S of Q, meaning that the supply depends on the quantity. Find the quantity supplied at a price of $5.25 per watermelon. Part C, find the equilibrium quantity and price for the watermelons. Let's start with part A. So to find the quantity demanded at a price of $5.25 per watermelon, we'll use the demand function that's given to us here. Now if the price is $5.25, we'll want to set that as P. So $5.25 equals 9 minus 0.75 Q. We want to know the quantity that's demanded at this price. So we solve for Q. So subtract 9 from both sides and divide both sides by negative 0.75, and we get Q is equal to 5. Now remember here that Q is the quantity in thousands demanded weekly. So 5,000 watermelons are demanded weekly. All right, part B is where we're talking about the supply of watermelons. So now you're given the formula for supply, and you are finding the quantity that's supplied at a price of $5.25 per watermelon. So we can set P equal to 525, set that equal to 0.75 Q, and solve for Q. Q equals 7, which means, again, remember Q is in thousands, so that means that the quantity supplied when the watermelons are set at 525 is 7,000 watermelons. Part C, find the equilibrium quantity and price for the watermelons. So equilibrium quantity and price means we have to find that equilibrium point. Now remember that that equilibrium point is really the intersection of the supply and demand lines. Since we have the equations for both supply and demand, to find the equilibrium quantity and price, we simply have to set the supply and the demand lines equal to each other to find the intersection point. So we'll take 9 minus 0.75 Q and set it equal to 0.75 Q. We'll solve for Q here, and we get Q is equal to 6. Remember, that's equal to 6,000 watermelons. Now that is the equilibrium quantity, but we still want to find the equilibrium price. Since we found Q is equal to 6, that means all we have to do is plug Q back into one of the equations. It doesn't matter whether it's supply or demand, because right now we know that this is the intersection point. They should both give you the same answer. Say I plug it in to my demand function. Then we end up with 9 minus 0.75 times 6, which is equal to 4.5. This is in dollars, so that means each watermelon is $4.50 per watermelon. And so this is the point where you won't have a surplus or a shortage of watermelons. Now another place where we use linear functions is in what we call cost analysis. So when we're talking about cost analysis, we're talking about when we are trying to manufacture an item, there are usually a couple of different things that determine the cost of manufacturing that item. So usually there are two parts. One is what we call a fixed cost, so cost that does not depend on how many items are made. So for example, it could be the cost of designing the product, setting up a factory, training workers, etc. But they are fixed costs. It doesn't depend on how many items you make. Then you have the cost per item. So cost that does depend on the number of items made. So this could be the cost of labor, right? The more items you make, the more labor is going to cost you. The more items you make, the more materials you'll have to use, so that is a cost per item. Packing, shipping, those are also examples where the cost of packing and shipping will depend on how many items are made. Now, when you're using a linear function to represent the cost of manufacturing, we typically will use B as the fixed cost and M as the marginal cost. So marginal cost is another way to talk about the cost of producing each additional item. So take a look at example 3. It says a small company decides to produce video games. The owners find that the fixed cost for creating the game is $5,000, after which they must spend $12 to produce each individual copy of the game. Find a formula for the cost as a linear function of x, the number of games produced. So we know that the fixed cost is $5,000, so that might be paying the people to create the game, design the game, get the video game music in there. But then the $12 to produce each individual copy would be maybe the shipping cost for each individual game. Perhaps it is the packaging for each individual game. So those are things that would account for the marginal cost, this $12 that's being spent on each individual one. So to write the formula, we would use mx plus b, where m is going to be the marginal cost, so anything that's going to be changing depending on how many of that game is going to be produced, and b is going to be the fixed cost, which is everything leading up to being able to create that game. So this is going to be, well, it's $12 for each individual copy, so 12x, and then plus 5,000. Let's do another example. The marginal cost to make X batches of a prescription medication is $10 per batch, while the cost to produce 100 batches is $1,500. Find the cost function given that it is linear. So in this case, you actually don't know what the fixed cost is. You're going to have to figure that out. So we do know that the marginal cost is $10 per batch. So we can start there. Now what we do know is that to produce 100 batches, it's going to cost $1,500. So what we can do is we can plug this in for x and c of x, and then solve for b. So we have 1,500 equals 10 times 100 plus b, which means that b must equal 500. So here it's asking for the cost function, so this would be c of x equals 10x plus 500. Now that we know how we can use linear functions to help us with cost analysis, the next step in cost analysis is actually to talk about break-even analysis. When we talk about break-even analysis, we have to first understand revenue and profit. So revenue is going to be the total amount that is made, whereas profit is the difference between the revenue and the cost. So revenue is in total, this is how much was made, but profit means that we take out how much it cost us to get there, and whatever is left over is how much we actually made, how much we actually profited. So a company will break even when the revenue and the cost are equal. Now obviously you don't want to just break even, but it is important to understand where that break-even point is. So the break-even quantity is the number of units at which revenue will equal the cost. Let's take a look at an example. A firm producing poultry feed finds that the total cost in dollars of producing and selling X units is given by C of X equals 20X plus 100. And the total revenue is given by R of X equals 24X. Management plans to charge $24 per unit for the feed. That's actually what the revenue is showing us, 24X. Part A, how many units must be sold for the firm to break even? B, what is the profit if 100 units of feed are sold? And C, how many units must be sold to produce a profit of $900? So let's start with Part A. How many units must be sold for the firm to break even? In other words, when does the cost end up equaling the revenue? Well, this is actually pretty straightforward for us to solve. We are given a formula for the total cost, 20x plus 100, and we're given a formula for the revenue, which is 24x. So we'll break even when those two are equal to each other. So set them equal to each other and solve for x. We have 4x equals 100, which means x is equal to 25. So how many units must be sold for the firm to break even? 25 units. Once you hit 26 units, then you're going to be actually making a profit. But at 25 units, you are breaking even. You will no longer be in the negatives in terms of what you're gaining. Now, Part B. What is the profit if 100 units of feed are sold? Now, how do you find the profit? The profit is whatever the total revenue that you get is minus the cost. So I'm going to first start off by coming up with that expression. So the profit, I'm going to call P of X, is equal to the revenue minus the cost. The revenue here is 24x, and the cost is 20x plus 100. The one thing you want to make sure is that you put the cost in parentheses. The entire thing has to be subtracted. All right, so simplifying this down, we end up with 4x minus 100 for the profit. Now it's asking what is the profit if 100 units of feed are sold? So we end up with 4 times 100 minus 100, which is equal to 300. So the answer here is $300. Part C, how many units must be sold to produce a profit of $900? Well, we already have an expression for the profit, 4x minus 100, and so we want this profit to equal $900. So now we solve for x to figure out how many units have to be sold. So we add 100 to both sides, divide both sides by 4, and we get x is equal to 250. So 250 units must be sold in order to produce a profit of $900.